We will now consider a circuit containing capacitors in series and in parallel and find the amount of charge that accumulates on the plates of those capacitors. The techniques we employ here will be very similar to the techniques used in the two previous examples. Instead of combining resistors, we are now combining capacitors, and instead of using Ohm's law to relate the voltage drop across a resistor to the current flowing through a resistor, we use Q equals CV to relate the voltage drop across a capacitor to the amount of charge that accumulates on the plates of that capacitor. Here is the circuit we are beginning with. At this point, pause the video and see if you could combine these three capacitors into a single equivalent capacitor that's connected to a 10-volt battery. I could draw my circuit to look like this, and when I do so, I see very explicitly that the 10 and the 5 microfarad capacitor are in parallel with each other. Combining these two capacitors in parallel, we add their capacitances. So I could say for these two capacitors, C equivalent would be 10 plus 5, which is equal to 15 microfarad. Before I proceed, there's one comment I would like to make. We said previously that normally when you start a problem, you want to convert all the terms to the standard SI units. So why did I not convert to farads up here? If you look at these two equations, C equivalent will always be in the same units as the capacitances on the right-hand side, as long as all the capacitances on the right-hand side are in the same units. By not converting to farads, I don't need to worry about carrying around powers of 10 to the negative 6 throughout my calculation. So it makes my work a little bit easier just not to convert. You can if you want, but you're making a little more work for yourself. So after we do that, we will have a single circuit with two capacitors in series. We'll have a 10-volt battery just like before. So here is my 10-volt battery. And then we will have a 15 microfarad capacitor and a 4 microfarad capacitor. And now that we have two capacitors in series, we could combine these. So I would say 1 over C equivalent is equal to 1 over 15 plus 1 over 4. If I look for common denominators, I could say 1 over 15 is the same as 4 over 60, and 1 over 4 is the same as 15 over 60. And I set that to 1 over C equivalent. And therefore, 4 plus 15 gives me 19. So I could write this as being equal to 19 over 60. And when I flip the left-hand side, I flip the right-hand side as well. So that tells me I could say C equivalent is equal to 60 over 19, which is equal to 3.16. And because we are working exclusively in microfarad, this term will be in microfarad as well. Now that we have a single capacitor connected to our 10-volt battery, we know that there will be a voltage drop of 10 volts across the plates of this capacitor. Using Q equals CV, we could find the amount of charge that accumulates on the plates of the capacitor. I could write Q is equal to 3.16 times 10 to the negative 6 times 10, and I find the charge that accumulates on the capacitor plates is 3.16 times 10 to the negative 5 coulombs. Before I proceed, there is a comment I would like to make about the value of the capacitance we plugged in here. When we combine the capacitors in series and in parallel, all of the capacitances were in microfarad, and since all the capacitances were the same, it was okay to do that. However, now that we are using Q equals CV, we want the capacitance to be in farads because we are working with coulombs and volts. Now that we have found the charge that accumulates on the plates of this capacitor, we will move one step backwards in unpacking our circuit. So I will have a 10-volt battery that is connected to a capacitor of capacitance 15 microfarad and a capacitor of 4 microfarad in series with that 15 microfarad capacitor. If you recall the derivation of the equivalent capacitance of capacitors in series, we said that the charge that accumulates on capacitors in series will be the same. That implies that there will be this much charge on this capacitor and on this capacitor. If we know the amount of charge that accumulates on these capacitors, we could calculate the voltage drop across these capacitors. So that's what we're going to do. Now that we know the charge that accumulates on both of these capacitors and we have their capacitances, we could again apply Q equals CV, this time to find the voltage drop across these capacitors. Looking at the 15 microfarad capacitor, I could write 3.16 times 10 to the negative 5 is equal to 15 times 10 to the negative 6 times V, and I find the voltage drop across this capacitor will be 2.1 volts. For the 4 microfarad capacitor, I could apply the same equation, and I would get 3.16 times 10 to the negative 5 is equal to 4 times 10 to the negative 6 times V, and I find the voltage drop across the 4 microfarad capacitor to be 7.9 volts. Notice that the sum of these two voltage drops is the same as the voltage of the battery. Now that we know the voltage drop across the 15 microfarad capacitor, I could expand that capacitor into a 10 and a 5 microfarad capacitor that are in parallel with each other. Because we have two circuit elements in parallel, the voltage drop across these circuit elements will be the same, and it will be 2.1 volts. Now I could apply Q equals CV to each of these capacitors individually to find the charge that accumulates on those capacitors. So I could write Q is equal to 10 times 10 to the negative 6 times 2.1, and I find the charge that accumulates on the 10 microfarad capacitor will be 2.1 times 10 to the negative 5 coulombs. And for the 5 microfarad capacitor, I could write Q is equal to 5 times 10 to the negative 6 times 2.1. And I find the charge that accumulates on the 5 microfarad capacitor is 1.05 times 10 to the negative 5 coulombs. At this point, we are finished with the problem. We found the charge that accumulates on each of the capacitors in our circuit. A charge of 3.16 times 10 to the negative 5 coulombs accumulates on the 4 microfarad capacitor, and these charges accumulate on the 10 and the 5 microfarad capacitor. Notice that the sum of these charges is equal to the charge that accumulates on the 4 microfarad capacitor, because when capacitors are in series, the charges that accumulate on them will be the same. If you really add these numbers, they are off by 0.01, but that is due to rounding.